Friends, good morning. Professor T.N. Oza here. In a new video on gaseous state of matter, we will be discussing today some aspects based on question answer type model. So this will be very useful and easy to understand. Please be careful. First question reads, calculate the density of carbon dioxide gas at 0 degree Celsius temperature and 1 atmosphere pressure. The answer is like this. Density rho is given by molar mass of the compound m divided by molar volume at NTP. Thus, density equal to 44, which is molar mass, grams per mole, 22.414 liter. So the answer comes 1.963 kilogram per mole. This type of question, very simple, but a practice is required. Second question reads like this. Calculate the mean free path of O2 gas molecule at 25 degrees Celsius and a pressure of 10 to the power minus 3 millimeter mercury column. Second part of this question, do the same at 1 atmosphere pressure given the collision diameter of oxygen gas is 361 picometer. Calculation is done as follows. First we convert pressure given in millimeter to Newton meter square scale. Calculation is then we calculate the mean free path lambda 1 equal to average velocity over under root 2 into average velocity into pi d square into P over kT. P is pressure, K is Boltzmann constant, T is absolute temperature, pi d square is cross section area, and C average is average velocity. When we put the relevant values in the equation, the result comes out to be 53.3 millimeter. At 1 atmosphere pressure, when we do similar calculation, we find that mean free path lambda 2 is much smaller. Means at higher pressure, mean free path decreases enormously. Third question reads like this. Calculate molar mass of gas if 560 cubic centimeter weighs 1.8 gram at NTP. Very simple. First we determine the molar mass. Formula is mass of given volume into molar volume divided by given volume. Simply put the values 1.8 gram into 22,414 cubic centimeter per mole divided by 560 cubic centimeter. Result comes out to be 72.05 gram per mole. In this question, temperature and pressure corresponded to NTP values. If the values are different, then first we have to obtain the value at NTP by using the formula P1 V1 over T1 equal to P2 V2 over T2. So please be careful. Fourth question reads like this. Calculate the volume V of carbon dioxide gas at 25 degrees Celsius and 765 torr pressure that is required to produce 200 gram of calcium bicarbonate by its reaction with calcium hydroxide, assuming 100% yield. Very simple, very interesting question. First we write the stoichiometric equation, calcium hydroxide plus 2CO2 giving calcium bicarbonate. Then we find their mass ratio. We add up the weights of fractions. So calcium hydroxide 74, 2CO2 88, calcium bicarbonate 160. The calculation reads like that: 88 gram multiplied by 22,414 cubic centimeter per mole, divide by 44, and we get volume at NTP, volume of CO2. Calculation of volumes P2 of CO2 at 25 degrees Celsius, 765 bar pressure for 200 gram of calcium bicarbonate. Using the formula P1 Vm over T1 equal to P2 V2 T2, or V2 equal to P1 Vm T over P2 T1. Putting these values which are already given, we find that we require nearly 60 liter of CO2 for completing the reaction, having the required amount of product. Question 5 reads like this. Calculate the number of moles of N2 gas contained in a 50 liter vessel at 25 degrees Celsius at 700 torr pressure. The number of moles of N2 gas in 22.414 cm cube at NTP is 1. Therefore, number of moles in 50 liter is calculated as follows. Using the formula P1 V1 over T1 equal to P2 V2 over T2. First we obtain volume at NTP, which comes out to be 42.19 cm cube. So divide this by molar volume, that is 22.414 liter per mole. The result is 1.88 moles. Question number 6. Calculate the energy E of an ideal gas per mole and per molecule at 30 degrees Celsius. Second part of this question, do the same for one molecule of H2 gas at 47 degrees Celsius, and third part for 2 gram of O2 gas at 47 degrees Celsius. Translational kinetic energy of ideal gas is given by 3.2 RT, where R is universal gas constant, T is absolute temperature. When we put the values of R and T in the equation, result comes out to be 3778.7 joule per mole. You can convert it into kilojoule by dividing with 1000. Energy per molecule, simply decide the energy per mole by Avogadro number, which is 6.022 multiplied into 10 to the power 23 per mole. Result comes out to be 6.275 into 10 to the power minus 21 joule per molecule. For a molecule of H2 gas at 47 degrees centigrade, using the same formula, 3 by 2 RT for one molecule, divide by Avogadro number, result comes out to be 6.63 into 10 to the power minus 21 joule. If we consider all the degrees of freedom, 3 for translational, 2 for rotational, and 1 for vibrational, then we use the formula energy equal to 7 by 2 into kT. Putting the values of Boltzmann constant K and temperature T, we obtain 1.546 to 10 to the power minus 20 joule per molecule. It may be noted that for diatomic H2 molecule, there are 3 translational degrees of freedom along X, Y, and Z axis, each contributing half kT. There are 2 rotational degrees of freedom, one about the Y axis, one about Z axis, each contributing half kT, and one vibrational mode contributing 1 kT. So the sum comes out to be 7.2 kT per molecule. Similar calculation for 2 gram of O2 gas at 2 gram means 2 or 32 mole. Assuming ideal behavior, use the formula 3 by 2 kT, divide the whole thing by 16. So the result comes out to be 2.49 into 10 to the power 2 joule. Considering all degrees of freedom as we done for H2 molecule, the result is 581.98 joule per molecule per 2 gram of O2 gas, not per molecule. Question 7. Determine the possible number of translational, rotational, and vibrational degrees of freedom for methane, ethane, benzene, carbon monoxide, and hydrogen sulfide molecules. First, we learn the theory. An atom, which is regarded as shapeless mass point for mathematical convenience, it has 3 degrees of translation, one each along x, y, and z axis. On the basis of this analogy, an n-atomic molecule should be expected to have 3 translational degrees of freedom. However, when molecular models are examined, it emerges that an n-atomic molecule has 3, not 3n whole body motions called as translational degrees of freedom. These are not quantized and involve small energy changes. In addition to that, molecules, but not atoms, also possess rotational and vibrational degrees of freedom. For example, a diatomic molecule AB placed along say x-axis can rotate about an axis passing through the center of gravity of the molecule and parallel to y-axis. One more axis is possible parallel to z-axis. So linear molecules have 2 degrees of rotational freedom. Non-linear molecules have 3 degrees of rotational freedom. A diatomic molecule also has vibrational degree of freedom coincident with the bond axis. It is only 1. For other molecules having more than 2 atoms, if it is the shape is linear, there are 3n minus 5 normal vibrational modes. If the shape is non-linear, the data is 3n minus 6. By a normal vibration, we mean that all the atoms of the molecule are undergoing vibration with the same frequency and all of them pass through their equilibrium simultaneously. It is to be noted that in addition to the normal modes, molecules also execute several overtone vibrations with varying probability resulting from combination and multiplication of normal frequencies. However, these are of much lower probabilities. In brief, we can say that a molecule will have 3 translational degrees of freedom, 3 rotational modes if nonlinear, 2 if linear, 3n minus 6 vibrational modes nonlinear, 3n minus 5 for linear shape. These are the degrees of freedom. Translational degree of freedom as explained before. If the velocity of the atom is c square, it can be shown that c square is the sum of the square of components, that is cx square plus cy square plus cz square. And the components of kinetic energy will be half mcx square plus half mcy square plus half mcz square. Means energy of translation equal to component energy summed ex plus ey plus ez. Rotational degree of freedom. Linear molecules have 2, non-linear molecules have 3. Formula is rotational energy equal to I omega square, where I is the moment of inertia given by mu r square. Mu is used mass, r is the radius of the circle run during rotation. Formula for reduced mass Ma into Mb over Ma plus Mb, where M refers to atomic mass. Atomic mass is divided by the relationship atomic weight divided by Avogadro number. This gives the mass of one atom. Vibrational degree of freedom. A diatomic molecule undergoes bond stretching, bond compression. This becomes one vibration. So if there are only two atoms, the shape could be linear only, and only one vibration is possible, that is bond stretching. If the number of atoms is more than 2 and shape is linear, then total 3n minus 5 normal vibrations are possible. Of these, n minus 1 are stretchings, 2n minus 4 are bending. However, majority of molecules are non-linear. For them, the total number of normal vibrations are 3n minus 6. n minus 1 is stretchings and 2n minus 5 bendings. Bending modes are also called deformation because the shape of the molecule is changed during bending. We can calculate the stretching vibrational frequency for a diatomic molecule assuming classical model, rigid model, comes out to be frequency in terms of reciprocal centimeter 1 over 2 pi c divided by under root f over mu. U is reduced mass, f is stretching force constant which is related to bond strength, and c is speed of light. This classical formula has some deficiencies, but for most of the practical purposes it is okay. Here I have shown how a diatomic molecule stretches and compresses. Hence, the rotation of AB type 2 modes and ABC type molecules 3 modes and variations in angular water molecule are shown in the following diagrams. The diatomic molecules has 2 rotational degrees of freedom, and for triatomic molecule like water, degree is 3. Regarding vibrations, H2O molecule which is nonlinear, the symmetric bond stretch is shown, antisymmetric bond stretch is shown. The bond bendings 3 modes are shown just for explanation purpose. Actually, for water molecule, only one bending mode is practically possible, and it is always in plane because 3 points always lie in a plane. Here I have collected degrees of freedom for some n atomic species. First column reads species, helium, hydrogen, H2O, xylene, benzene, CO2. Second column reads number of atoms, the species 1, 2, 3, 4, 12, 3. The third column gives shape, H2, xylene and CO2 are linear, benzene and water are non-linear. For each of these, including helium, translational degrees of freedom is 3, rotational is 0 for helium, 2 for H2 and CO2 and styrene, 3 for water and benzene. Vibrational degree of freedom 0 for helium, 1 for H2, CO2 has 4, benzene has 30, styrene has 7. The last column gives total number of degrees of freedom 3 for helium, 6 for H2, 9 for H2O, 12 for styrene, 36 for benzene, 9 for carbon dioxide. Principle of equipartition of energy. Energy E equal to 3 by 2 kT equal to sum of components E plus Ui plus E. Assuming equal contribution from these three components, we have Ex equal to Ey equal to Ez equal to one third of the Dy 2 kT equal to half kT. Conclusion. Each degree of translational and rotational freedom available to a molecule contributes proportionate amount, half kT per molecule, to the kinetic energy. Because vibration imparts both kinetic and potential energies, contribution is 1 kT per mole per molecule. For example, water molecule contributes 3 half kT for each of the three translational modes, 1 half kT for each of three rotational modes, 1 kT for each of three vibrational modes, totaling 6 kT. We have also calculated similar for H2, CO2, acetylene, helium atom for further understanding. Next, we embark upon a very important topic, Maxwell distribution of molecular velocity. The famous physicist Maxwell derived this formula in 1860. It is still valid. Gas molecules are randomly moving and frequently colliding one another and with the walls of the container vessel. During collision, transfer of energy between molecules takes place, which causes changes in their velocities. So there is a whole range of velocities. Let us consider probability du being in the range u and u plus du. So it can be shown that bu is proportional to e raised power mu square by 2 into kt, 1 by kt, where mu square by 2 is energy. Proportionality constant can be put pu du equal to a e raised power mu square negative over 2 kt du. Constant of proportionality a can be evaluated by putting probability equal to 1. Remembering that the parameter u has both direction, integration of equation between limits negative infinity to plus infinity leads to equation given below. And thus we calculate a equal to under root m upon 2 pi kt. Therefore, du du equal to under root m upon 2 pi kt divided by exponential factor e raised power minus mu square over conversion to three dimension by using the relationship P U V W equal to PU into P W. Here U V W correspond to probabilities along each Cartesian axis. Solving further, we derive the expression, probability expression, dc or dn over n, where n is the total number of molecules. dn over n is the fraction having velocity in this range c and c plus dc range. Formula has been derived as equation 5 for one molecule. Molar scale, same formula becomes equation 6. We have to replace small m by capital M molar mass, and we have to replace Boltzmann constant by universal gas constant. Distribution of molecular velocities has been shown in this diagram clearly. Most probable velocity, average velocity, root mean square velocity. Effect of temperature on distribution of molecular velocities. If we look at equation number 5 or 6, both equations are similar. What we find, temperature T is in denominator, but there is a negative sign. Means part of equation shows that at higher temperature, most probable velocity increases and the whole graph is shifted towards right hand. One more thing, the exponential part of the equation number 5 and 6 called Boltzmann factor. polar scale. This factor is very much useful in spectroscopic discussions and also in chemical kinetics. Type of molecular velocities, concept of variable velocity. In a previous video, we have given details about this. Here we are repeating it. Three kinds of velocities are recognized: root mean square velocity, average velocity, and most probable velocity. Using Maxwell equation, these equations can be derived. Equation for most probable velocity is under root 2 kt over m. For average velocity, under root 8 kt over pi m. For root mean square velocity, under root 3 kt over m. The ratio of these three velocities, that is CR root mean square, CAV average, CMP most probable, is 1 ratio 0.92, ratio 0.82. Similarly, C average ratio CMP is 1 0.886. Now we embark upon another point, related point. Maxwell distribution of molecular kinetic energy. A fraction of molecules Dn upon n having translational kinetic energy in the range of epsilon plus dc. As we know, energy per molecule is given by mc square over 2. It means c square is 2 epsilon over m, or c equal to under root epsilon over. On differentiating, get 2c dc equal to 2m over 2m 2 over m into dc d. It means c dc equal to d over m. Therefore, we can put the value of c square dc as c into c. This manner, derive the value for c square. Substituting the value of c square dc in Maxwell equation derived earlier, we obtain the fraction of molecules having energy in this given range by equation number 16b. The numerical problem solving the application of this equation has been included here. For O2 molecule at 1 atmosphere pressure, 300 Kelvin temperature, we have calculated the fraction of molecules having velocity in the range epsilon minus 0.005 epsilon, epsilon plus 0.005 epsilon. In this case, O2 molecule has molar mass 32 gram per mole. For one molecule, divide this by Avogadro number, and by putting the data and doing the necessary arithmetic, we obtain value of fraction of molecules having velocity in that given range. Comes out to be 4.647 into 10 to the power minus. Can be shown that most probable translational kinetic energy per component by Z is given by kT over 2 molecules RT over 2 mole inverse. Kinetic energy given by 3 by RT. Heat capacity of an ideal gas. Molecule stores energy owing to translational motion, rotational excitation, vibrational excitation, electronic excitation. According to Born-Oppenheimer, total energy of molecule can be taken as the sum of these fractions of these components: translational, rotational, vibrational, electronic. At normal temperature, electronic component is omitted, and also our vibrational contribution, mostly 20% value is taken, not whole percent. But in this video, we will be doing calculation 100% just for simplicity. Examples of CV: Here Cv and Cp both have been defined. Cv is del E over del T at constant V. Cp is del V over del T at V. It means Cv total is equal to Cv translational component plus Cv rotational component plus vibrational 20%. For some molecules, we have calculated Cv at room temperature. Helium, result is 12.47 joule per Kelvin per mole. HCl, result is 22.45 joule per Kelvin per mole. CO2, result is 27.44 joule per Kelvin per mole. In solid phase, P vibrational is considered but not the translational and rotational. One more thing, the relation between Cp and Cv is Cp equal to Cv plus R. And one more factor, the ratio Cp over Cv is called gamma. Calculate Cv, Cp and Cp by Cv for water, CO2, H2 and CH4 now. In this, what we have to do? First, we have to decide each degree of freedom, translational, rotational, vibrational. For translational, contribution to Cv is 1 by 2 of K, 1 by 2 R on molar scale. Similarly, for rotational, 1 by 2 R, and for vibrational, 1 R. By putting the values, we can calculate contribution to Cv for the given molecule. During the calculation of degree of freedom, we should be careful about the shape of the molecule, about the number of atoms in the molecule. Another example, H2, CO2. One more example for calculating Cp and gamma of helium gas. Cv is 3RT by 2. It means Cp is 5R by 2. And Cv is 3R by 2. There is a small mistake. Cv I have given 3RT by 2, which is not, T is not there, it is 3R by 2. And Cp is equal to 5R. Gamma is 1.66. For methane gas, gamma is 1.02. We have to estimate Cv for some of the molecules below: argon, neon, HBr, USCO, and one more question. At what temperature will the Cr of SO2 gas be equal to the Cr of O2 gas at 27 degrees Celsius? Very simple question, full level question. Question is solved like this. Cr of SO2 or Cr of O2 is 1, is given by temperature for SO2 to molar mass of O2 divided by temperature for O2 per mass of O2. This manner we obtain the temperature value as 600 Kelvin, 327 degrees Celsius. Another very important, very interesting numerical is at 23-liter cylinder contains O2 gas at 17 degrees Celsius temperature and 4 atmosphere pressure. Some gas leaked out, and when the orifice was mended, inside gas pressure was registered to be 0.6 atmosphere. How much gas was leaked? Very simple question. You see in this question, T is constant, V is constant. Only pressure is changing, number of moles is changing. So what we do? First we calculate the theoretical volume at NTP. Then we calculate again theoretical volume at NTP after leakage. Difference of both volumes gives the amount of gas which leaked. Convert it to number of moles by dividing with molar volume. We obtain the result as 2.513 moles. Number of moles leaked 1.353. How does the mean free path in a sample of gas vary with temperature, constant volume, rigid container? Coordinate equation is given here. It shows that at V constant mean free path is independent of temperature. Question number 13. Given the coefficient of viscosity of certain gas, CO2 gas, 14.80 micropoise, 93 Kelvin, calculate its origin diameter. Formula is 2 under root mRT over 2 pi cube to 2 pi 3 by 2 into Na into d square. Here m refers to molar mass. Just by putting the values of m, r, t, pi, Na, evaluate d. Here in the last question, I have noted down some short questions whose answers are available in both videos, this video and the previous one. You have to write the answers for practice purpose. That will be very useful for you. In this way, we have concluded this video. Thank you very much for watching. I hope if you practice these numerical problems, you will learn a lot about the gaseous state. Please like, share and subscribe to my video chemistry channel. Again, my good wishes for all of you. Thank you. Thank you very much.